Welcome to The Explainer. Today, we're looking at an absolutely massive shift in the AI landscape. If you've been managing enterprise AI scaling recently, you already know that performance is really only half the equation. The other half, the constraint that actually matters when you're deploying to production, is cost. So we're going to unpack how the arrival of Deepseek V4 acts as this unbelievable cost-saving lever, fundamentally changing what is economically viable for your tech stack. Okay, let's dive into this with a quick boardroom-style roadmap of what we're covering. We're going to start by breaking the AI cost barrier, then unpack the architecture of efficiency and mastering the million token context. From there, we'll look at bypassing hardware supply constraints, comparing DeepSeek head-to-head with proprietary giants, and finally, rounding it all out with enterprise deployment trade-offs. Section 1. Breaking the AI cost barrier and the staggering API cost difference. Anyone out there running massive automated code audits or vast document analysis knows the intense, very real financial pain of skyrocketing API costs. When you scale up to thousands of requests a day, well, the infrastructure bills can completely explode. Just look at this jaw-dropping figure, 14 cents. That is the cost per 1 million input tokens for the DeepSeek V4 Flash model. To put that into perspective, you're talking about a fraction of a cent for processing entire books or massive code repositories. It's an undeniable financial shock, and it's literally forcing the entire industry to pay attention. Now, what's really interesting about this data is the sheer scale of the gap between these models. Take a look at the output costs. Claude Opus 4.6 sits at $75 per million output tokens. DeepSeek V4 Pro, their flagship model, sits at just $3.48. That is a massive fraction of the proprietary model's costs. Suddenly running daily AI audits on huge code bases or letting an autonomous agent just iterate through endless loops of testing, it isn't just an experiment anymore. It's completely 100% economically viable for everyday enterprise operations. Moving right along to Section 2, the architecture of efficiency, we really need to talk about how their mixture of experts design achieves this trillion-parameter scale so incredibly cheaply. And it isn't magic. It's just brilliant, localized efficiency. The model has a total capacity of a staggering 1.6 trillion parameters. But the secret sauce? Only 49 billion parameters are actually active per token. Think of the mixture of experts architecture as a surgical query of specific expert layers. Rather than firing off a massive computational shotgun blast across the entire network for every single word it generates, it only activates the exact 3% of the neural network it actually needs at that moment. But here's the catch. A massive parameter count doesn't mean anything if the model can't learn efficiently. Enter the muon optimizer. This is a second-order optimization technique they used instead of the standard AtomW. To put it simply, this optimizer ensures that the massive 1.6 trillion parameter count actually translates to real-world reasoning capability rather than just looking good on a spec sheet. It's absolutely crucial for stabilizing training at these extreme scales. Section 3, Mastering the Million Token Context. This is all about solving the infamous KV cache memory problem. We all want to feed, say, 15 novels into an AI at once, but historically, standard memory scales quadratically until your compute nodes literally just crash. DeepSeek solves this using multi-head latent attention, essentially splitting attention into two distinct mechanisms. And this brilliantly illustrates the approach. First, there's compressed sparse attention, which compresses the footprint by 4 times for high-fidelity, precise retrieval. Then there's heavily compressed attention, applying a massive 128 times compression for broad, wide-angle context awareness. By interleaving these two layers, the model gets selective detail and broad awareness, without that exponential, compute-crushing cost of full attention. And the result of that hybrid architecture? 10%. At a 1 million token context, V4 Pro requires only 10% of the KV cache memory footprint compared to its predecessor, V3.2. It completely solves the bottleneck that used to make ultra-long context just way too expensive to actually use. Okay, Section 4, Bypassing Hardware Supply Constraints and how frontier AI is running on domestic silicon. As we know, due to US export restrictions, cutting-edge NVIDIA hardware is restricted in China. The implications of DeepSeek optimizing for domestic hardware are pretty profound, and they were neatly summarized by NVIDIA CEO Jensen Huang, who noted, quote, "The day that DeepSeek comes out on Huawei first, that is a horrible outcome for our nation," end quote. This statement highlights a significant industry milestone. Deepseek V4 acts as a major validation for the domestic Chinese hardware ecosystem, proving that the CAN software stack and Ascend supernodes are completely viable alternatives for running frontier-level AI. When we compare the hardware directly, something really fascinating emerges. The NVIDIA H100 draws around 700 watts of power. The Huawei Ascend 910C draws significantly less, at just 310 watts. Now, while the Ascend chip has lower raw memory bandwidth than NVIDIA's flagship, Deepseek's hyper-efficient architecture and hybrid attention compensate for this limitation entirely. They've built software that truly thrives on specialized, constrained hardware. Let's move to Section 5 and see how this builds into Deepseek versus proprietary giants with some head-to-head performance metrics. Looking at the benchmarks, Deepseek V4 Pro is standing toe-to-toe with GPT-5.5 and Claude Opus 4.7. In the SWE Bench Verified Coding Test, it hits 91.2%. On Human Eval and Math 500, it is right there in the mix. Yes, for sure, it trails the absolute bleeding edge by a few percentage points, representing roughly a 3 to 6 month gap, but it operates in the exact same frontier tier for complex coding and math, all while functioning at 10 to 13 times lower output costs. So the crucial point here is understanding the exact trade-offs. Open-weight models like V4 aren't perfect yet. They still trail proprietary models in a few key areas. If you need a model to follow highly intricate, multi-constraint formatting instructions perfectly, or you're running long-horizon agentic tasks that require 50 or more sequential steps without losing focus, while closed-source models like Claude Opus 4.7 definitely still hold an edge. V4 also lacks native multimodal integration right now and has a different safety and refusal profile that your compliance team should absolutely review. Which brings us perfectly to our final section, Section 6, Enterprise Deployment Trade-offs. This is where we look at self-hosting versus strategic routing. Because V4 is released under a highly permissive MIT license, you basically have a choice. First, there's self-hosting. This guarantees complete data sovereignty and privacy, which is absolutely perfect for healthcare or finance. But running a 1.6 trillion parameter MOE model requires steep hardware capital, often between $50,000 to $200,000 or more. Alternatively, you have the API. This offers zero upfront capital expense and those ultra-low recurring token costs we discussed earlier. But, of course, you're relying on third-party infrastructure. For most smart enterprise teams, the answer isn't choosing just one vendor, it's hybrid routing. Step 1. You route your massive 1 million token context tasks, like daily repository audits or processing thousands of PDFs, straight to Deepseek V4. Step 2. For those rare high-complexity, multi-constraint tasks that require flawless 50-step agentic reasoning, you route to Claude or GPT. This optimizes your total expenditure without sacrificing any quality. I want to leave you with this final, slightly provocative thought. When frontier-level reasoning costs just $1.10 per million output tokens, the old rules simply don't apply anymore. Is your scaling constraint still your AI budget? Or is it now just the imagination and architecture of your application? It is truly time to fundamentally rethink your tech stack. Thank you so much for joining me on this explainer, and keep building.